So the piece I'm going to perform is slightly unusual for me because most of my work has been focused on the human voice, both as an improviser and as an electroacoustic composer, and as a programmer, because it's very difficult to deal with the voice. It's a very complex signal. But this piece is like a return to my roots. For various reasons, I was asked to participate in a project with scientists to somehow see if we could work together on a research project. Now that didn't quite work, but what I did do, I decided to make a piece using scientific data. Was it possible to make music out of scientific data? Now the first problem with this is that the scientific data may be really interesting from a scientific point of view, but that doesn't mean to say it's at all interesting musically. And in fact, I wrote lots of programs that would convert data into pitch, into control files, into filter coordinates, into spatialization, everything. But in the end, most of the results just sounded random. It would have been the same if you put random numbers in. So my first thing was, what data has some kind of structure that might lend itself to music? And I came up with two things. The first was Supernova Explosions. Now these are very, very interesting scientifically. They're also very significant to us because of the nature of stars. When stars form all the chemical elements up as far as iron, then iron is very stable and the star dies. But there are lots of elements beyond iron in the periodic table which we are dependent on as living things. They're part of us. So how are these made? Well, they're actually made in supernova explosions. That's the only place we know they're made. So poetically, this is quite significant. But the next problem is how to turn the data into sound. So essentially, I take the light spectrum of this explosion, which lasts for 64 days. I decided a piece lasting 64 days might test the listener too much. So I shortened that to 9 minutes. And then it wasn't completely straightforward to convert the light spectrum into sound. There's various complications. If you're not careful, you just end up with noise. But I figured out a method eventually to convert the interesting information in the spectrum, in fact the peaks and the troughs, which actually indicate the presence of elements being generated in the supernova, and convert those into sound. And these sounds move through you in the space, in sound surround. And at the end of the piece, because the supernova generates these elements, but it gets very, 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 shall we say, in terms of sound, extremely quiet, inaudible. So at the end of the piece, I decided to use the spectra of the elements as emerging from the sound of the supernova. So that's the first piece. The second piece, I know everyone's already done this, but an obvious thing to do is to work with chaos. How do you make a piece which is not simply chaotic? So the piece has two kinds of material. The first kind of material is to do with something called the Logistic Equation, which is a very simple description of population dynamics, of a predator and its prey, and what happens in the balance of the population. And mathematically you can show that if you push the environmental conditions, eventually the relationship becomes chaotic. So the material at the beginning and the end of this piece, this is called Signatures of Chaos, is this gradual emergence of chaos. And this is done by mapping the population fluctuation as melodic lines, essentially. There are lots of other complications, but I won't explain those. Now in the centre I work with another kind of chaos, which is turbulence. In fluid flow, when you see a very calm-looking river, this is called laminar flow. But when it's flowing over rocks or it's buffeted by the wind, you get something called turbulent flow. And what's interesting is the way you move from laminar flow, smoothness, into turbulence. And there's a particularly interesting phenomena here. If you spin a liquid around, it begins and looks completely smooth. And then at a certain speed, it starts to rotate in little bands like this. Whoops, I can't do this. Like this, against each other. And then those bands themselves start to become turbulent. And finally, the whole thing becomes turbulent. And this thing is called Taylor-Couette flow. So what I've tried to create is an analog in sound surround of this kind of fluid flow and the gradual breakdown of the fluid into turbulence. And then I was stuck. I couldn't think of any other material to use that had this kind of structure. I couldn't find anything that really interested me when I was approached by the Ness group at the University of Edinburgh, who were making physical models of musical instruments. Now, by a physical model, they don't mean what you might think. What they mean is a description in a computer in a precise physical way of what the instrument does. So how long is it? What exactly is its shape? Where are the valves? How many are there? How far down? What is the air pressure? What is the tension on the lips? What's the weight of the lip? Everything, absolutely everything. Now, the first problem with this is, of course, if I want to use, say, a brass instrument, it's easier to use a microphone, so why bother? The answer is, what if I want a brass instrument that's a kilometre long, or one that has 16 valves, which are all being played at once, which happens in this piece, or one in which the lips are incredibly stiff and heavy, so they're not human, or the pressure is the pressure of a jet engine, or in fact in this piece twice the pressure of a jet engine sometimes. You can do all that with a physical model. If you, of course, for example, if you blow it, don't put enough air pressure in, it won't make a sound, just like a physical instrument wouldn't. But you can do these things that, in theory, could exist physically, even though they don't. So, and the poetic of this piece is, at the time, we just began to discover these Earth-like planets. And I wondered, what would it be like if we arrived at one of these planets and we could walk on the surface, we could breathe and all those kind of things. So clearly the air pressure would be the same. The laws of physics would be the same. So there could be music. But what we don't know about this music is not only the cultural things, how they would make music, but also their instrument technology. So let's make a piece, an imaginative piece, of a welcoming ceremony for brass and percussion instruments, all imaginary, on the planet Kepler 63c.